So in the previous video, we saw that there are two problems that are related to implementing the switch using an NMOS transistor. The first problem was the slow charging of the capacitor. As V output increases, VGS is going to decrease, which will cause the current charging the capacitor to decrease as V output is increasing, which will take long time to charge the capacitor. The second problem is once the voltage of the capacitance at the output, the parasitic capacitance at the output reaches VDD minus V threshold, the transistor will be off because VGS will be less than V threshold. The transistor will be off and the capacitor will stop charging at VDD minus V threshold, which we called poor one problem. And we said that this poor one problem causes other problems. For example, if you connect the output here with the poor one to a CMOS inverter, then both transistors, the PMOS and the NMOS, will operate together, causing power dissipation. How to solve these problems? The first solution is circuit-based solution. The first method is circuit-based. So they do a connection, a circuit connection, circuit-based solution. They do a circuit connection to keep charging the capacitor up to VDD. So instead of making the capacitor stop at VDD minus V threshold, they will do a trick here using some other additional connection in the circuit in order for the capacitor to continue charging. What is this trick? So if this is our switch, and we connect here high, and here for the second input we connect high, okay? Then this is the output. This is the capacitance. What they will do is they will connect here a CMOS inverter. They connect here a CMOS inverter with VDD, and then they will take the output of the CMOS inverter and they will connect it to a PMOS transistor. And this PMOS transistor, they will connect it like this. So let me try to clarify this a little bit. This is our output, V output, this is our capacitance. What they will do, they will take the output, they connect it to an inverter. And then they take the output of the inverter. So let's call this V output 1, this is V output 2. They will take the output of the inverter, they will connect it as a control to the gate of a PMOS transistor. And then the PMOS transistor is connected up to VDD, and down they will connect it to the capacitor. How would that connection solve our problem? This connection can solve our problem because if you assume that in the beginning the voltage here will reach to VDD minus V threshold, which is the poor one. What will happen is, although this is a poor one, but it will cause the output of the CMOS inverter to be low, 0. It will be 0. And you can see that by checking the curve of the CMOS inverter that we studied before. Okay, although VDD minus V threshold, it's not high, it's not VDD. Okay, this is the input, this is the output. Although the input is not high VDD, it's poor one, it's poor high VDD minus V threshold, but still the output is going to be 0. So when the output here of the CMOS inverter is 0, it will go here to the PMOS transistor, and the PMOS transistor, if its input is 0, then it will be on, and when it is on, it will charge the capacitor. It will allow current to pass from this supply to keep charging the capacitor until the capacitor reaches VDD. So again, I'm going to say it again. Here, assume that in the beginning we have a poor one problem, VDD minus V threshold. VDD minus V threshold will go as an input to the CMOS inverter. But the CMOS inverter, if the input is VDD minus V threshold, still it will give you the output to be low. So the output here will be low. When this low output goes as an input to a PMOS inverter, the PMOS inverter operates when its input is low, okay? Because VSG will be high. If the gate is low, VSG will be high, so the transistor will be on. And when the transistor is on, it will allow current to flow from the supply here, VDD, towards the capacitor, and the capacitor will keep charging until it reaches a voltage of VDD. So this is the first method to solve the poor one problem, is circuit based by connecting a CMOS inverter in addition to a PMOS transistor. Okay, the PMOS transistor here is called the weak PMOS. This PMOS transistor is called weak PMOS. Okay, this is the name that is used to describe this transistor, and this is a circuit-based solution to solve the poor one problem. However, as you see, in this solution we have a feedback, right? We have a feedback from the output towards the input. This positive feedback causes some additional problems, some more involved problems. So it's not as simple as we described here. The feedback will cause some other problems, which makes this solution not as practical as we wish. Okay, so the feedback, usually any circuit with feedback, usually it has some stability problems, it has some problems due to the feedback. So we are not going to discuss the details of these problems in our course. However, you have to know that the feedback causes some additional problems, which makes this solution not practical. The second solution, or the second method to solve this problem, is technology based. So the second method is technology based. And technology based, I mean, by using the technology, we can try to implement the switch using an NMOS transistor that has a threshold voltage of zero threshold voltage. And they can do that by controlling some properties of the semiconductors that they use to implement the transistor. So they can control the threshold voltage by using something called natural devices. Natural devices, they have this threshold voltage to be with threshold voltage to be 0. If the threshold voltage is 0, then your problem is solved, because if the threshold voltage is 0, the poor one, which is VDD minus V threshold, will be VDD, and we solved the problem. Okay, so we have first method is circuit based by doing a connection like this with a feedback, some feedback problems. Second method is using natural devices, and these natural devices are just transistors, but they control the threshold to be 0, exactly 0, and then the problem is solved. The third method is, instead of implementing the switch using the NMOS transistor, they implement it using the transmission gate. So the third method to solve this problem is, instead of implementing the switch using the NMOS, we implement it using the transmission gate, and we'll see now how the transmission gate solves this problem. So let's now discuss the transmission gate and see how the transmission gate solves the problems related to the implementing the switch using NMOS. So as we said, transmission gate consists of two transistors, NMOS and PMOS, to implement only one switch. So in order to implement one switch, we use two transistors. So the transmission gate looks like this: NMOS and PMOS. And if you connect here the input to high, and again here we said that in NMOS you connect your input, and for the PMOS you connect your inverted input. So if you connect high here as your B, okay, VB, Then here you will connect VB bar, which will be 0. Then this is the out. And let's assume that this is the capacitance, the parasitic capacitance at the out. Let's see what happens here, how we solve the problem of poor 1 here. Let's assume that in the beginning the output was 0 in the beginning, okay? And we connected here our two inputs, high and high. So what will happen is we have an NMOS transistor, PMOS transistor, so let's see the terminals. For the NMOS transistor, this terminal is connected towards the high, so this is the drain, right? So this is the drain of the NMOS, this is the source of the NMOS, and of course this is the gate. For the PMOS, the terminal that is connected towards the high is the source, and the one connected towards the low is the drain. So this is now the source, while here this is the source of the NMOS. Now, because VGS here in the beginning, VGS in the beginning is VDD minus 0. In the beginning, I'm going to write the beginning using the red color. Then this transistor will be on in the beginning. And again, here, let's look at the PMOS transistor. VSG of the PMOS transistor is VDD minus 0. So VSG is big, it's larger than V threshold. Then this transistor will be also on. And the capacitor is going to charge through both transistors. So the capacitor is going to charge through both transistors, right? Because this transistor is on, it will allow current to flow. This transistor is also on, it will allow current to flow. Until the capacitor reaches, and let's do it in blue color, until the capacitor reaches VDD minus V threshold N. Once the voltage here at the capacitor reaches VDD minus V threshold N, VGS will be exactly V threshold N, right? Because it will be VDD minus V threshold N, and this transistor will be off. The NMOS transistor will be off. So there is no current that will come from the NMOS transistor. However, let's look at the PMOS transistor. The PMOS transistor, VSG will remain as it is, because VSG doesn't depend on the voltage of the capacitor. VSG will remain constant, equals to VDD. So the PMOS transistor will stay working as it is exactly, and the capacitor will keep charging. The capacitor will keep charging through the PMOS transistor, because the PMOS transistor again, VSG equals VDD, always VDD, regardless of what is V out, because V output is connected to the drain here. So VSG of the PMOS transistor will always remain as VDD, and the PMOS transistor will always stay on and will keep charging the capacitor until the capacitor reaches to VDD. So the capacitor will be allowed to charge up to VDD, and once it reaches VDD, there will be no current in the PMOS, because the source is already connected to VDD and the drain will be VDD. So there will be no current flowing through the VGS will be 0, or VSD will be 0. So there will be no current anymore in the PMOS, and the capacitor will stop at VDD. So the capacitor will charge up to VDD, and the poor 1 problem disappears. So again, what happened here is when the NMOS turned off, at the point where the capacitor voltage reached VDD minus V threshold, the NMOS turned off, but the PMOS stayed working as it is, and the capacitor kept charging through the PMOS. Like, let's take the other case when we put our input to be low. So here, let's see if there will be any problem in the other case. This is our NMOS, this is our PMOS, this is our capacitor, and let's assume in the beginning that the capacitor, it had a voltage VDD, and let's assume that here the second input is high VDD, here VB bar will be 0, And then we are going to connect our input A to 0. This is the opposite case. So here we had the two inputs high and high, so the capacitor had to charge from 0 to high. Here we'll take the opposite case. The capacitor is already high, but we'll connect the input to low. Of course, in this case, the case that we are plotting, we are having the output to be the end between the input, and the output is the ending between A and B, right? The output will be high if A is high and the switch is controlled by high, right? That's why if high and high, the output is supposed to be high. If low and high, the output is supposed to be low. But now let's start that the output at the beginning is high, and you are going to connect the input here to low. Now let's look at the terminals. Let's look at the terminals of the transistor. This is NMOS, and this terminal is connected to low, so this will be the source. This terminal is connected to high, this will be the drain. This is a PMOS. This terminal is connected to low. For the PMOS, this is the drain. And this terminal is connected to high, this is the source. So this is the source of the NMOS, and this is the source of the PMOS. In the beginning, VGS, of course this is the gate, this is the gate. VGS here, VGS is VDD minus 0, so it's VDD. So this transistor will be on. VSG here, VSG of the PMOS is VDD minus 0, VDD. So in the beginning, both transistors will be on, and what happens is that the capacitor is going to discharge through both transistors. The capacitor is going to discharge. Until when? Until the voltage of the capacitor, reaches V threshold. Until V output, the voltage of the capacitor reaches V threshold. And here we assume that V threshold N equals negative V threshold P. Okay? So until V output equals VT. Until V output reaches V threshold. Once V output reaches V threshold, we'll do it in blue. Okay? V output reaches V threshold, then VSG will be exactly V threshold. So this transistor will start to turn off because VSG will reach exactly V threshold. So this transistor will turn off, and the capacitor will not be able to discharge through this transistor anymore. However, this transistor, VGS of this transistor doesn't depend on the voltage of the capacitor. So VGS of this transistor will remain always VDD minus 0, to remain always VDD, and this transistor will remain on, and the capacitor will keep discharging through this transistor until it reaches 0. So the capacitor, during the discharge, it will discharge up to here. Starting from here, the NMOS transistor, here in this region, both PMOS and NMOS are on. Starting from this point, the PMOS will be off, but the NMOS will be on. So starting from this point, PMOS will be off, but the NMOS will stay on, and the capacitor will keep discharging until it reaches 0. Here, the capacitor was charging, right? The capacitor was charging. So it will, in the beginning, it will charge through both transistors until it reaches VDD minus V threshold. So both transistors here, NMOS and PMOS, both of them are on. Starting from this point, once the capacitor voltage reaches VDD minus V threshold, the NMOS will be off, and the PMOS will stay on, and the capacitor will keep charging up to VDD. So that's how the transmission gate, when we implement the switch using the transmission gate, we overcome the problems that we faced in implementing the switch using the NMOS transistor. okay? Especially or specifically the poor one problem. We'll see in the next video some examples on using the transmission gate to implement the different logic gates. See you in the next video.